Welcome to Lesson 10C, Mean Age and Effectiveness Coefficient. We're going to talk about something called mean age, and there's also a parameter called the effectiveness coefficient that we'll discuss. By way of intro, in real life, there's no such thing as perfectly well mixed. We've always assumed in all our problems so far that the room was perfectly well mixed, and we draw this fan and say that a concentration anywhere in this room is the same, but in real life that's really not the case. So what do? Well, HVAC engineers have come up with some parameters to quantify how well a room is well mixed. You can say quantify well mixedness. First, TN, capital N, is called the characteristic time of a room. And so we're talking about a room here. And Tn is defined as 1 over n. Remember, n is the number of room air changes. So if you recall, n was equal to Q over volume of the room. So supply flow rate over volume. Therefore, Tn is just 1 over n, or V over Q. Physical explanation for this is Tn is the time to displace an entire room volume of air if there is ideal displacement ventilation. What I mean is this: if you have ideal displacement ventilation, suppose you had a clean room where you're bringing in flow from the bottom and it comes right out the top perfectly evenly, so you have kind of a piston of fresh air that's coming in, and in one room air change, it displaces the entire volume. And that's what it actually means then. So Tn would be the same time as it takes to remove all that stale air. So that's an ideal case for displacement ventilation. A real room would be nothing like that. Some clean rooms come close to that. But a real room in the USA, we typically have some inlet or supply and some outlet. These are typically both in the ceiling. I'm sitting in my office, and that's what I see here. I have a supply coming in one location and an outlet or an exhaust coming out at a different location, both in the room. So that's pretty typical. And you have a diffuser to kind of push this around instead of just coming straight down. And then it's sucking out air through the exhaust like that. So what happens is you get some big eddies in this room, and you might get some recirculation in here like that, and you get a lot of turbulence and stuff mixing up. Even if there's no fan, you're still going to get something like that. So what we're going to do is pick some point P in the room, and we'll put sensors there so we can do some analysis of that. We're going to define a couple more things here. Let's define local mean age, T age at point P. The local mean age is the average time it takes for a fluid particle entering the room through the supply inlet to reach point P. Let's again draw our room, and we have some in and some out supply and exhaust. What is T age? First, let's define our point P here. The air may take some circuitous route. It doesn't necessarily get to P directly. And so the time it takes to go from the supply to point P is what we're calling the local mean age. We say average time because you do this once and then you do it a second time. It's doing maybe a long path sometimes and a short path sometimes. So it's the average T age P. There's also something called residence time. You start at P, the local residence time, T residence P, is the average time it takes for a fluid particle to go from P to the exhaust. Mean age is entering the room and going to P, and then P out is the residence time. So this would be T residence at point P. And you could pick other points, and you'll have different values for these guys. A few comments here. See text for details and the equations for how to do this. How do you measure this? You typically inject a tracer gas, and that could be SF6 sulfur hexafluoride or helium, which are very non-toxic chemicals. And then you measure C as a function of T at point P, and then you use the equations in the book. I'm not going to go through that. The TH one, this left-hand side, the THP is the one that's more important to us for what we're doing. Then what we define is another parameter, which is what we really want, and that's this E, which is called an effectiveness coefficient. And E is equal to Tn, this characteristic time that we defined, V over Q or 1 over N, divided by THP. and the units of E are 1. In other words, it's unitless. Tn is a global property. It's a property of the whole room. 1 over the number of room air changes. That's a room property. It has nothing to do with where you're at in the room. Whereas P is a local property, and that's at a point. And you can do this at various points in the room then. And let me talk about what this effectiveness coefficient means. It's Tn over THP. We'll do 3 cases. If E is equal to 1, so in other words, THP equal Tn, what that implies then is mixing at this point P is the same as a well-mixed case. So if you happen to get E equal 1, even though P is just some point here in the room, you would have the same mixing at that point as if you had a well-mixed room with a huge ceiling fan mixing everything up. And you happen to pick a point where that's true, this point P. So that would be E equal 1. If E is less than 1, which means THP is greater than Tn. Remember, the THP is on the denominator, so that means it's bigger than Tn on the numerator. And that means that mixing at P is not the same as, but smaller than the well-mixed case, or in other words, it's a slow response time. THP is bigger. It takes longer to mix things up and get to a certain concentration of fresh air compared to the well-mixed case. Finally, if E is greater than 1, it's the opposite. THP is less than Tn, so mixing at P is larger than the well-mixed case. This means a fast response time. HVAC people find this useful. Well, the usefulness is to identify points in the room that have poor ventilation. And we'll define poor ventilation as E less than 1. So it's this case up here. You have a long THP, and therefore you have poor ventilation relative to other points in the room. Why is that important? Well, let's again look at our room. We have in, we have out. Again, there's usually some big eddy in a room like this. You'll also get some recirculation pockets of more stagnant air in these corners, and you'll have a lot of turbulence overall too. So let's just arbitrarily pick a couple points in here. A at this location, B at this location, and C somewhere in the middle here. Suppose we're at A, directly under the inlet or supply. So we expect that EA is greater than 1. In other words, it's a fast response, whereas B is in a corner, and this would be a recirculation. In fluid mechanics, we call that a recirculation bubble, an eddy that's kind of spinning around. And EB we expect to be less than 1, but has a slow response. So we would say that B has poor ventilation. You might have some point where E equal 1 at C. That does not mean that the room is well mixed. It just means that at this point, E happens to equal 1. It's the same as it would be in a well mixed case, but the whole room itself is not well mixed. So keep that in mind. And as far as practical application, if this were an actual room and there's COVID around, I would much rather be sitting at A than B because I get that fresh air right near me. It's a very fast response. So I'm not likely to get infected by other people in the room. Whereas in B, you might be in a little more trouble. Let's do a quick example. We have a ventilation system in a room. I give the volume, and we cover this whole room in plastic wrap to remove any infiltration or exfiltration. Wall losses are negligible in this room. We supply 450 CFM into the room, and we use helium or SF6 the way we talked about to measure TH at A and B. And these are the values given. Well, let's calculate the effectiveness coefficient and then discuss the implications of it. First, we calculate Tn. The characteristic time is V over Q, the given volume over the given volume flow rate. That gives you 12.8 minutes. And then at A, we have EA, by definition, is Tn over TH at point A. That's the effectiveness coefficient at that point, 12.8 minutes over 4.63 minutes. Of course, the minutes cancel there, and we get 2.76 equal EA. And similarly at B, you get 0.520 equal EB when you just plug in 24.6 minutes instead of 4.63 minutes. I also asked for the implications. A has good mixing and a fast response time, and B has poor mixing and a slow response time.
That reminds me of my brother here. He has a slow response time too. So do you. I'll prove it.
In terms of the quality of the air, I would rather be at A than at B, assuming that you're getting nice, fresh, clean air from the ventilation system.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.